All right, the problem of the day. There's a lot of talking going on here. All right, problem of the day, we had to identify stereocenters. How many of you guys felt pretty comfortable identifying stereocenters? All right, so most people did. I'll kind of breeze through this. If we look at albuterol, it's got a stereocenter on that carbon. And if we look at Prozac, it's got a stereocenter at that carbon. Aspirin, on the other hand, does not have any stereocenters. A couple of you guys noticed some tricks, too. If you see any sp2 hybridized atoms, they can't have stereocenters, right? They don't have 4 different groups attached. So you're only looking at the tetrahedral or sp3 hybridized atoms. Just ignore anything that's in a benzene ring. All right. Today we're going to talk a lot more about chirality. But in this case, I was looking for you guys to match up the idea that molecules that have stereocenters are oftentimes chiral, meaning they've got both a left-handed form and a right-handed form. We saw on Monday that sometimes one of those forms can be therapeutically useful, the other form can be quite toxic or lethal. And the next question was asking how many stereocenters were in each of these molecules. We had 1, 0, and 1. And then question 2 is the tricky one. First thing we need to do is identify our stereocenter. So I'm going to identify that there. Next thing I really like to do is draw in the assumed hydrogen. So there's an assumed hydrogen off of that carbon. Is it a straight line, a dash, or a wedge? Wedge. That carbon's tetrahedral, so this hydrogen has to be sticking out towards our eye, right? So we can draw that in just to keep track of it. Then we can go through and assign priorities. Oxygen beats the 2 carbons that are attached, so we can label that as priority 1. Now we've got a problem. We've got a carbon here, and we've got a carbon there. Which one's higher priority, the left or the right? The left. And a good strategy for this is what I do is I make a little list. If we think about that carbon, it's attached to a sulfur. It's attached to a carbon on the other side, and it's attached to a ghost carbon. So we do SCC. And then the next one, what's that carbon attached to? Carbon, hydrogen, and hydrogen. So when you make this list, make sure you list it in order of atomic size. So you notice I started with sulfur and not carbon. And then we went for carbon first and then the 2 hydrogens. When you're comparing these 2 groups, what you want to do is compare the heaviest of each. So sulfur beats carbon, right? All right, so we could label this position 2 and this position 3. Draw our arrow around from 1 to 2 to 3. It's going to the right-hand side, right? Or clockwise. So normally that would be an R, but what's the problem here? Yeah, hydrogen's pointing towards us. So in this case, this would be an S stereocenter. So remember that you have to flip the R versus S rules if your lowest priority is pointing towards you and not away from you. Does that make sense? Yep. All right. Let's go back to chapter 5 and go back to the issue of chirality that I was bringing up. What do you guys think it means to be chiral? Yeah, some of you guys read ahead. That's great. All right. Chiral molecules are non-superimposable on their mirror image. So the way I like to describe this to people is, like I said yesterday, look at your left hand and right hand. They're mirror images of one another, but if you try to overlay them, there's no way that you can get them to overlap perfectly, right? They're different because of that. So let's take a look at this with an example molecule. Got a carbon here, hydrogen sticking up, fluorine out here, and a chlorine going back. would this be considered a chiral molecule? Yeah, and the way you can check if a molecule is chiral or not is draw a pretend mirror. So that's my pretend mirror. And then redraw the mirror image of the molecule. Are these the same molecules? They look the same, just like our left hand looks like our right hand. But if you spin it around, they don't overlap perfectly if you try to superimpose them. So in this case, they're non-superimposable mirror images, which means that it's chiral. And so what chemists call these two, when we draw the mirror image of a molecule and they're non-superimposable, we call them enantiomers. And we're going to talk a lot more about classifying pairs of molecules, but this is directly related to chirality. These are a pair of enantiomers. Let's try to assign R or S to the one on the left. What's going to be highest priority, bromine, chlorine, or fluorine? Oh, which one's the biggest atomic number? Bromine. All right, so we'll label bromine as 1. What's the second highest? Chlorine.
And the fluorine and the hydrogen.
All right, and then we label that as 4 if we want. All right. Sometimes our hydrogen's tricky to spot, right? So is this R or S, and how can we determine it? We got to play a little bit of mental gymnastics. Let's pretend I'm laying down on the floor, looking up underneath this. Is the spinning going clockwise to the right or counterclockwise to the left? Imagine yourself laying underneath this molecule looking up. The chlorine's sticking back, the bromine's going out. The bromine's here, it goes counterclockwise, right? So bromine's above me, chlorine's over here, and I'm spinning it like that. So think about it in your head, it should be counterclockwise. So imagine underneath, bromine's sticking straight up, right? Chlorine's over here.
What is the straight element that we are going to rotate it?
We're looking at bromine going to chlorine to fluorine. Can you guys see how chlorine's pointed straight up? Chlorine's going into the board. So imagine you guys are looking at me. Bromine's up here, chlorine's to my left, fluorine's to my right. So we're going counterclockwise, right? So sometimes you do have to do that mental manipulation.
Is it 1, 2, 3 or 1 or 2?
Were there questions in the back?
Yeah. Why do we look at it?
Because in this case, we want to place our lowest priority going backwards behind the carbon. That makes it easiest to determine R versus S. So if it's going counterclockwise, we're going to our left. Would that make it R or S? S. Sometimes this requires building a model kit, right? This is why model kits can be your best friend with chiral molecules. It's because it gets really hard to visualize these in 3 dimensions, right?
So which direction will you go? The 1, 2, 3 direction or 1, 4, 2 direction?
So basically I'm going underneath like this. So imagine looking up.
So just 1, 2, 3 directions.
Oops. Yep.
You can just say the atom and then you know, you don't have to.
Okay. What's the R or S designation for its enantiomer? So now we can go underneath and we can look at it and we can say, all right, bromine's up, we're going over to chlorine, and then back around to fluorine, so now we're going clockwise to the right. So the enantiomer is going to be R. Enantiomers are basically the same molecule, but the stereocenter has been flipped from R to S or S to R. That's one of the easiest ways to spot enantiomers. All right, the interesting thing with these enantiomers is how they behave. If I took the compound on the left and I measured its melting point or boiling point or any of its physical properties, it'd be the exact same as the compound on the right. It's pretty crazy. I think it's crazy. You guys might not. Enantiomers have the same physical properties. Just like your left hand has essentially the same properties as your right hand. They can do roughly the same things. Same things with these molecules. They behave the same in terms of their intermolecular forces, polarity, you name it. They're identical. So the question is, how do chemists distinguish between one chiral molecule, one enantiomer, and the other chiral molecule, its partner? It's pretty weird. So how can we tell them apart? What's that?
Like, why are chiral molecules important? Like, is it more than just one's toxic and one could be beneficial in medicine?
Yeah, so imagine you take your house key and you get the mirror image of your house key. Is that going to open the lock on your door?
Yeah.
No, right? Imagine the groove is on the left on your normal house key. And then when your mirror image, it's going to be on the right. It won't fit into your lock. So chiral molecules, the way they interact with enzymes is like a lock and key mechanism.
Yeah.
If you've got the mirror image of it, it's no longer the right key for that lock.
Okay.
And that's why sometimes we run into these severe problems with having the wrong enantiomer of a drug.
So is it correct to say that enantiomers are stereoisomers or stereoisomers?
Yep, they're stereoisomers. And we're going to talk about all the classifications of these, but this is the first and most important one, is enantiomers are non-superimposable mirror images of one another. Yep.
Are enantiomers going to be on the exam?
Yeah, anything that we're covering this week could be on the exam. We're going to practice them with the in-class activity tomorrow, though. All right, so how can we tell them apart? Chiral molecules rotate plane polarized light. So what I have here is the equipment that's used for determining chirality. You have a light source. If you think about light, it's a wave, right? It goes up and down. A normal light bulb, these waves go in every and all direction, right? You can have them up, down, side, side, diagonal, left and right. That's non-polarized light. Polarized light, what you're doing is filtering out all of the wavelengths except one's going in a particular direction. So we put in a filter or a polarizer so that we get only one wavelength of light out. It's going straight up and down in this case. So we've got this light that's going straight up and down, and then we've got a film of our molecule, almost like with an IR. And that light goes through the molecule, and when it goes through that molecule, the chiral molecules will actually cause that polarization, instead of going straight up and down, to actually spin a little bit in one direction. So chiral molecules will change how that polarized light travels through a sample. So you can see it's going through this tube and hitting an analyzer. So it may have gone in going perfectly vertical up and down, and it comes out looking somewhat diagonal. What we're measuring is that angle. How much did it rotate? Did it rotate 10 degrees? Did it rotate 5 degrees? Did it rotate to the left? Did it rotate to the right? And that's how we can tell these molecules apart.
So if it be the same if they were trans and cis,
Say that again?
would it be the same effects you get who are this trans or cis?
No, we're going to talk about that later. That's a different classification called Diastereomers, and we're going to talk about that later. But right now we're focused just on mirror images of molecules. Trans and cis molecules aren't perfect mirror images. Yep. All right. So it's an interesting thing It seems super complicated. It's not too bad though. Let me move this up. All right, so what chemists need to do oftentimes in order to avoid poisoning people is we need to make a molecule that's pure, right? We need only one-handed version of a molecule. We don't want the other-handed version. So we need to make sure that we're making only that one-handed version. And so what chemists do is they use polarimeters to actually study whether or not they made their molecule correctly or not. And let's talk about how that works. So chemists struggle to make enantiomerically pure compounds. Another way of thinking about that is oftentimes the sample is contaminated with the opposite hand. The opposite-handed version. So chemists need to come up with a system using the device shown above in order to measure how pure our compound is. Is it 99% pure? Is it 80% pure? I mean, it has the same boiling point. The only way we can tell it apart is how it spins that polarized light.
When you say pure, that only with one mirror image,
Mm-hmm.
it's not pure.
Exactly. Let's say I'm trying to make a left-hand version of a molecule. I could have 99.9% left-handed and then one right-handed version in there. So we need to be able to come up with a system for measuring what's the ratio of our left-handed version to our right-handed version. And this is a really big deal with chemists. If you make the wrong-handed version of a drug, like I said, it could potentially cause some seriously bad side effects. So they use a system called enantiomeric excess. And so the way they do this is they first take 100 and then they multiply it by the observed rotation. And for rotation, I'm going to use this alpha symbol. And we divide that by the rotation that's expected for a pure enantiomer. And this gives you your enantiomeric excess, which I call EE percent. So let's take an example of this. So let's say I've got a compound and its normal observed rotation in its pure form is 15 degrees. So it takes that polarized light that's going straight up and down and it bends it by 15 degrees after it travels through. But our sample that we made only rotates at 10 degrees. Let's do this calculation. So the example is the pure should be 15 degrees, but our sample is 10 degrees rotation. Let's figure out its percent EE. What do you guys think it would be? It'd be 100, 10 divided by 15. Yeah, we could say, let's even round it to 67%. I'll put the period after here so we're keeping track of our sig figs.
I have a question.
Mm-hmm.
Do you mean the rotation like, I don't know if you know rotation,
degrees.
Yeah, exactly. So imagine the light's going straight up and down. It goes through your sample, and when it exits your sample, it's going diagonally. How far off the vertical is it going? So we measure it going straight up and down to that vertical. That angle, in this case, would be 10 degrees for our sample that we measured. Ideally, it should have been 15, though. So we're just measuring what's the angle that that light was spun. Was it spun 90 degrees, meaning is it now going horizontal? Was it even spun 180 degrees, going all the way up and down vertical opposite direction? How far along that range did it go? Yep.
Just a curiosity question. So, if you have to have drugs be pure with this, do they have a way that they can either filter it or only make one-handed compounds?
That's what we're going to talk about next.
Okay.
But let's first talk about what the 67% actually means, right? So let's think about this. We've got 67% of our pure enantiomer. What's going on with the rest of it? It's a mixture, right? So what we would say is that we've got 33% of a racemic mixture. So we've got 67% pure, 33% is racemic, meaning it's an equal mixture of both hands.
Why would that?
So we just measured that 67%. We're saying it's 67% absolutely pure. The remainder is a mixture, whatever's left behind.
But isn't a mixture of the pure enantiomer?
Exactly. That's why oftentimes people get confused with enantiomeric excess. So if we break down this racemic mixture, what would that be? It'd be 16.5% pure or correct enantiomer. And then it'd be 16.5% wrong enantiomer. Let me even rephrase this to say pure/correct. So if we go through and we add our pure percentages together, it's not that we only have 67% of our pure enantiomer. It's that we actually have, what would that be? I'm terrible with math. 67 plus 16.5, 83.5. Our sample is 83.5% correct enantiomer. And 16.5% incorrect. So do you think if we're a drug company and we've got a sample that's 16.5% impure, that that's a very good thing? No, that's a very bad thing. Yep.
Will it always be 50-50 like that?
Yeah, exactly. So that was the next thing I wanted to point up, is do you think a racemic mixture is going to rotate plane polarized light? No, it's kind of weird. So imagine your correct enantiomer. We've got our wave going up and down. It's spinning it to the right. Our incorrect enantiomer will actually spin it to the left to the equal degree, right? So the correct enantiomer might spin it to the right 15 degrees. The incorrect enantiomer will spin it to the left 15 degrees. So if you've got a 50-50 mixture, those two cancel out. And so racemic mixtures are optically inactive and that's why they don't get counted into this calculation at all. And that's why we have to do a little bit of extra math. So remember that racemic mixtures are optically inactive. So I heard somebody say, well, how in the heck can we purify these things if they have the same physical properties? We can't do distillation, right? We can't separate them based on differences in polarity. What are we going to do? There's a few techniques that are around to try to improve this purity. One of them is called chiral chromatography. So what you do is you get a sorbent where you embed a chiral molecule in a column and then you put another chiral molecule through. One-handed versions of it will travel through it at a different rate than the other-handed version. We're not going to get into the nitty-gritty of it, but that's what a lot of pharmaceutical companies do. Alternatively, you can try to do selective crystallization, which is fairly tricky, and again, it's a more advanced technique, but I did want to tell you guys a little bit about them.
Could you explain what this means for the correct enantiomer and the wrong enantiomer?
So let's say we made a mixture of both left-handed and right-handed versions of the molecule.
Yeah.
And we calculated using our equation that it's got an enantiomeric excess of 67%. That means that we correctly made our molecule 83.5% of the time, and then 16.5% of the time it's the opposite-handed version of that.
Okay.
It's just telling us our ratio of the correct enantiomer to the incorrect enantiomer.
Okay, so the wrong one actually means the opposite one.
Yeah, it means the mirror image of it.
The one is same, is the opposite structure.
Yeah, it's the mirror image or opposite hand.
Okay.
Yep. It's pretty tricky, I know. We're going to now take a look at some other terminology. So we've discussed enantiomers, but let's make a little flowchart for this. Oops. So enantiomers versus diastereomers versus meso. What do all of these mean? Let's make a list. First one is enantiomers. What are enantiomers? Yeah, non-superimposable mirror images. They have the same physical properties, but how are we able to tell them apart? Yeah, with plane polarized light. I'm going to say PPL for plane polarized light. This is different than something called a diastereomer. A diastereomer is not a mirror image. But connected in the same way. And diastereomers, as my old professor at UO used to call them, he said they're cows and chickens. They're entirely different than one another. So diastereomers have different physical properties. All right, so let's take a look at the examples. And usually people can pick these up with examples fairly quickly. So let's take a look at 2 of them. All right, example 1. We've got OH up here, and we've got Cl pointed back. And my other molecule has a Cl here and an OH right here. Are these mirror images of one another? Oh. Let's try.
Damn it.
Let's flip this. We're going to flip it upside down. So like a pancake, not a chair flip. So imagine we're going to take the molecule on the right like a pancake, scoop it up underneath, flip it over. All right. The OH group, if we flip it perfectly over, is still going to be on the top, but is it going to be a dash or a wedge if we flip it over? It's going to be a wedge. So we've got OH. What about the chlorine? Is it going to be on the top left or top right if we're flipping it over like a pancake? Top left, and is it going to be a dash or a wedge? Dash. So we can pop in this chlorine. Now are they mirror images of one another? Yeah. So what we can say is these are now mirror images. Does that mean that these are enantiomers or diastereomers? Enantiomers. Enantiomers are always going to be mirror images of one another. Diastereomers are not mirror images of one another. So that's one easy way to tell. I'll show you guys the trick, though. So what I was asking you to do is to compare these 2 molecules, the one on the left. So compare molecule A on the left to molecule B on the right. Are they the same, different? Are they enantiomers or diastereomers? And so in this case, molecule A and B look the same, but they're different, just like our left hand's different than our right hand. So they're mirror images of one another, but they're non-superimposable mirror images.
So
Yep.
this is a diastereomers.
Yeah, it's an enantiomeric pair. Yep.
So A and B are still considered enantiomers.
Yep, A and B are still considered enantiomers. All we did with B was we flipped it over like a pancake to see if it truly was a mirror image. Do you guys want me to show you an easier trick? All right. Let's determine the stereocenter for this carbon right there that I labeled with green. Is it R or S? I'm hearing a lot of R's, which is correct because if we go up, we label this oxygen 1, this carbon would be 2, this would be 3. So if we draw our line around, it's going clockwise or to the right. The lowest priority, that hydrogen, is sticking back into the page. So we're twisting to the right. It's going to be R. Okay? So let's label this. I'm going to go through and I'm going to label this R. Now let's go through and label this carbon. Is that going to be R or S? So this time chlorine's position 1, this is 2, this carbon would be 3. So if we tried to connect it, it's going to the left. However, where's our lowest priority substituent? It's coming forward. That assumed hydrogen's pointing towards us. So is this going to be R or S? R. So let me fill this in. Do the same thing with compound B. Whoops. Compound B, what's this stereochemistry? Is it going to be R or S? S. What about over here? What's the stereochemistry over here?
I guarantee it does.
S. I like that. I guarantee it. That's confidence. So we've got R and R for compound A, and then in compound B we've got S and S. With enantiomers, one thing you can do is say if all of the stereocenters have been flipped, these compounds are enantiomers. That's one of the most reliable ways to go about distinguishing these. All of the stereocenters are flipped. So our R stereocenter in the enantiomer is S, and the R1 on the other carbon is also switched to an S. So they're entirely flipped, and that's how we can call them enantiomers. They're non-superimposable mirror images. They have the same physical properties, but they rotate plane polarized light differently. Yep.
So if you had one of the compounds that has like both an S and an R, the enantiomer would just be RS?
Yeah, exactly.
Okay.
Yep, it doesn't have to be RR, it could be RS. The important thing is that your R position gets flipped to an S in your enantiomer, and your S gets flipped to an R. Yep, so let's do another one. The next one I have for you guys are these two molecules. Actually, shoot, let me change one thing here. I apologize. Change this to a CL. I know. Everyone's huffing like, my perfect notes. Why are you doing this to me? All right, so if we look at these two, are they mirror images of one another? Well, let's try. Kind of like we did before. What I'm going to do is slide this over, and I'm going to say, all right, well, let's flip this like a pancake so at least it's oriented the same way. If we flip it like a pancake, will that methyl group on the top be a dash or a wedge? Be a dash, right? So if we flip it over like a pancake, the CH3 group will be a dash. What about the Cl? Dash, and it'll be on the left-hand side. So now, if we compare these two, we can draw our invisible mirror plane. These are not mirror images, which means that these will be called diastereomers. So you notice how the one on the left would be called trans, the one on the right would be called cis. Cis and trans, if we're comparing those, they're diastereomers, always. Yep.
So instead, oh wait, okay, no, I was looking at the wrong thing.
Okay.
The diastereomers, they have the same things coming off, like methyl one.
Yeah, so if we look at the ring, we still have a cyclohexane. So we have a methyl group coming off the top and a chlorine coming off the side. They're connected in the same order, but they've got a different layout in three-dimensional space. It's the same thing with enantiomers, but enantiomers are non-superimposable mirror images. Diastereomers are just not mirror images altogether. Yep.
What's the relation between the first molecule and the third molecule?
What do you mean the first and third? This one versus that one?
Yeah.
These two are the same
Yeah, I mean,
in the box.
left one and right one.
So if we're comparing these, they're considered to be diastereomers.
Oh, so the middle one and the right one are actually the same one?
Yes, the middle one and the right one are the same one. They're just flipped over. I took the molecule and flipped it like a pancake.
I mean, why you have to spell the third one?
So people could see that they're not mirror images. So you see that red dash that I drew?
So you
That's
mean-
my mirror plane. I'm trying to show that, in this case, the methyl group's not a perfect mirror image anymore.
Oh, so you mean that probably it's going to be a tricky question. You have to think about Flowchart or not.
Yeah.
Okay, I got
But
it.
I'll show you guys a trick just like I showed you for the last one. So with enantiomers, we said flip every single stereocenter, and you get your enantiomer. Let's take a look with diastereomers. What's the stereochemistry for this position? Is it R or S? It's R. So again, if you think about the highest priority, it's now this carbon because that carbon has a chlorine bonded to it. Second highest would be this carbon because it's bonded to another carbon. And then third one would be this carbon because it's bonded to 3 hydrogens. So if we go through, we're rotating to the right. Our lowest priority is pointing back, and so this would be R. Okay, let's do the other position that's got a stereocenter. It would be R. Class full of pirates. All right, let's do the same thing for the other one. What's this top one? It'd be R. Nothing's changed, right? It's a wedge in both of those. And then let's look at this chlorine over here. S. So with enantiomers, we flip every single stereocenter. But with diastereomers, we flip some, but not all of them. So you can flip 1, 2, or 3 if you've got 3, but you can't flip them all. If you flip them all, they become enantiomers, right? So let's make a little note of that. So they have some, but not all of their stereocenters flipped.
Could you do the middle one just so I can see the comparison? Because I want to know if like it's going to flip because those are diastereomers. But
Yeah, let's go through and look at this position right there. Highest priority would be here, 2, and then 3. So it looks like we should be rotating to the left, but our lowest priority is pointing forward. So this would be an R, right? So nothing's changed with that stereocenter when we flipped it upside down. Then if we look at this one over here, chlorine would be 1, then we've got 2, then we've got 3. So it looks like it should be an R, but the lowest priority is pointing forward, so it would be an S. So can you see how we haven't changed the stereochemistry for this molecule at all? All we did was flip it upside down. All right, there's one last curveball I got to throw at you guys. Meso compounds. They are considered let me rephrase this. They're molecules containing stereocenters that are superimposable. The way to tell is that they have an internal mirror plane. So let's take a look at an example of this, and I'll show you guys what I mean. I'm going to draw yeah.
Go back a little bit.
I'll draw a cyclopropane, and I'm going to put a CH3 group here, and a CH3 group here, and I'm going to compare that to this molecule where our CH3 group is a wedge, and this CH3 group is a wedge. So if we look at each of these, we could say, all right, there's a stereocenter here on this molecule, and there's a stereocenter here. So if we tried to draw the mirror image, the one on the right is a mirror image. But let's take a look at these mirror images. What if I took this molecule like this and I flipped it over? They're mirror images, but are they superimposable now? Yeah, these are the exact same molecule. So a lot of people would be tempted to say, well, these should be enantiomers. We flipped every stereocenter. But the problem is, even with flipping all of those stereocenters, the molecule is now superimposable. It's the exact same molecule. They're not. This is kind of our meso exception rule. It's a compound that does have stereocenters, but is achiral because it is superimposable on its mirror image. It's not superimposable. All right, the easiest way to spot meso compounds is, can you guys see that if I split this molecule down the middle, it's the same on the left-hand side as the right-hand side? It's got an internal plane of symmetry. Anytime you see molecules with stereocenters where it has an internal plane of symmetry and the left-hand side is the same as the right-hand side, you've got a meso compound on your hands. Same thing with this one. It's got that internal mirror plane, and we could say, well, if you take this molecule and you flip, we just get the exact same compound. So meso compounds are the last kind of exception to that rule. So when we classify things, we either say that you've got a pair of enantiomers, you've got a pair of diastereomers, or you have a meso compound. Yep.
So like people, are we like Enantiomers or Meso?
Oh man, I'd have to think about that. Let me get back to you on that. I'd have to think about that. This is a good question. Yep.
So like if we change one of the metals to like something else like chlorine, would it be an
Yeah, if we change one of the methyl groups to a chlorine, then we'd run into the case of having enantiomers. Yeah. Actually, I've thought about it. If you take a human being, we've got an internal mirror plane, so we are considered meso compounds. If you took a mirror image of me, I could superimpose myself on that mirror image. So human beings are meso compounds. Yeah. All right. Just 1 second. Make sure that if you